Hey guys, Ego here. Today we're going to be talking about the cross product. Last time we went over the dot product, and I actually did that first on purpose because I think the dot product actually lends itself a lot of uses in terms of explaining the cross product. Now, similar to last video, I'm not going to go over entirely all the proofs in this one just because it would take so long, especially when we talk about the magnitude of the cross product. That's a very big, long, kind of algebraic, heavy math proof type of thing. It's not necessarily hard, just long, and I don't necessarily know if I want to do in this video. However, Khan Academy has done one, so I will link that in the description. I highly recommend you watch it. You will be, you should be anyway, prepared for that video. I don't think he mentions anything that I haven't mentioned in terms of my video. I do think he talks a little bit about the dot product, but I honestly can't remember. I've watched it a long time ago. Anyway, let's get into it. So the definition of the cross product is that it returns a vector that is orthogonal. Orthogonal, meaning 90 degrees, to both vectors A and B. A and B. Okay, so it's going to return a vector that's orthogonal to both vectors A and B. So there's actually two vectors always that are going to fit that. So let's draw this out, right? So we have a very simple thing, right? Two vectors here. So a vector that would be 90 degrees to both of these would be one that goes out like this, right? So we have 90 degrees here, and we have 90 degrees here. But there's also a vector, complete opposite, that goes out like this. That also fits that category. So out like this, and out like that. And we'll talk about which one you're getting. This has to do, whether it's the one going out in this direction or the one going out in this direction. That has to do with the right hand rule, and it's very important that you understand it. But for now, we're going to focus on calculating this thing. So how do we calculate it? So calculating it is actually, it's going to look a little harder than it is. I promise it's not that difficult. But let's go through it. So it's going to be, let's say A cross B, and I'm just going to write this out and we'll explain it later. So we're going to say A sub Y multiplied by B sub Z minus A sub Z multiplied by B sub Y. And that's our X component, okay? And then we're going to say A sub Z multiplied by B sub X minus A sub X multiplied by B sub Z. And that's our Y component. And then our final component is A sub X multiplied by B sub Y minus A sub Y multiplied by B sub X. Okay, and those are three things. So this is, and I'll do this in, I guess, a slightly different color. This is our X value, our new X value for our A cross B. This is our Y value for A cross B. And this is our Z value for A cross B. And I'm going to actually show you mathematically what's the dot product, why these are in fact 90 degrees to either A or B. But first, let's actually go over how I have this, or I wrote this out, because I don't have a piece of paper. I did this out of my head, and you might be going, wow, well, you just memorized it. That's actually not the case. There's a pattern to it. So if we write these out, so we say A sub X, B sub Y, or sorry, I guess A sub Y, and A sub Z, and I'm going to repeat this again, A sub X, A sub Y, and A sub Z. I'm going to do the same thing with B, so B sub X, B sub Y, B sub Z, B sub X, B sub Y, and B sub Z. Right? Let's go over this. Let's circle some things out. So let's say AY times BZ. So let's circle these AY, BZ. So we can draw, okay, those two there. So we can draw a line between these two. Okay. And then the next thing, that's subtract. That's subtracting. What color can I use here? Sorry. That is subtracting AZ, BY. So AZ here, BY here. So let's draw a line between that. That's a cross. A cross for something called the cross product. I'm going to give you a little bit of a hint here. The name is actually derived from the pattern. that we're going to see. So if we do this, once again, that's AZ BX, so I'll use the same colors here. AZ times BX, right? Oops, should be using, no, that's right, sorry. AZ BX cross like that, and then AX times BZ cross once again, and then AX times BY, or subtracting AY times BX, right? So as you can see, the way I've done it anyway is that the red lines always come first, right? So AY BZ, AY BZ, AZ BX, AZ BX, AX BY, AX BY, and then we always subtract those from AZ BY, AZ BY, AX BZ, AX BZ, AY BX, AY BX. So if you can kind of memorize this pattern in your head, you can easily write it out. Of course, there's always going to be the cross methods in Studio anyway, so it's not a huge thing to memorize. It's just good to, have this calculation in your head, especially if you want to go over why the 90 degrees exists. But of course, you don't have to have this memorized. You do have this method in Studio, which I of course recommend, because why would you want to have to write out a function for this type of thing if you don't have to? So that goes over explaining actually the calculation. I want to then talk about how things are in fact 90 degrees. So what's a good color? I've been told not to use blue, so I'm going to avoid blue. Let's go with white. So in terms of proving that this guy is 90 degrees, so what I want to go over quickly is the dot product. So we talked in the last video about how the dot product is, vector A, the magnitude of vector A times the magnitude of vector B, multiplied by cosine of theta. Now we know just basic math, and we can also assume that the magnitudes of A and B for our cross product are greater than 0. So just keep that in mind. You can't cross a vector with a magnitude of 0. It just doesn't work, because if it's just at the center, then it has no direction. So how can you possibly say what's 90 degrees to it and what's not, what's orthogonal to it and what's not? It just doesn't work. So we can assume that both of these are greater than 0. So getting back to this, we know that if theta is 90 degrees, cosine of 90 degrees is in fact 0. So cosine of, I guess I'll do it like this, 90 degrees is equal to 0, like that. So because we know that, if we use our other dot method, the component method, which is AX BX plus AY BY plus AZ BZ, right? We know if this is not equal to 0, or if this is equal to 0, because these are the same thing, it's just a different way of calculating. If this is equal to 0, and once again we know that the magnitude of A and B is not equal to 0, then we know that the angle between the two must in fact be 90 degrees. And therefore these two things are perpendicular. So let's go ahead and dot this guy up here with A or B and see what we get, because I told you it's 90 degrees, so we should get a 0 degree or 0 dot product, because these two are orthogonal. So let's check it out. So just getting rid of this stuff. Okay, so let's start. So the dot between, so A dot A cross B, like that, right? So we're going to take the like components. So that's going to be, I'll just move this over a titch. That's going to be AX times AY times BZ minus AX times AZ times BY. And that's just that single X component dotted. Or X components dotted, so then it becomes AY times AZ times BX minus AY times AX times BZ, BZ, and that's our Y component, and then finally we're left with AZ times AX times BY minus AZ times AY times BX, like that. Right, so we have our, and I just want to zoom out, that's probably a bit too much. So hopefully you can see that. I guess you'll just have to remember that it's A dot B on that side. But what you'll see here is that these things actually cancel out. We're going to be left with 0. So let me pick a good color for that. So let's see, ax, ay, bz. So let's find a corresponding negative version of that. So that's ax, ay, bz. Let's see, ax, ay, bz, and there's our negative there. So these two, so this guy and this guy, are going to cancel out. So we can cross these guys out here. Bye-bye. And let's see if we can find some more things. So let's see, let's look for a positive ay, az, and bx. Let's see, ay, az, bx. So these two, this guy here, sorry, not that guy, this guy there and this guy here. So these cancel out over here. And then I'm sure you can already see by now, but we'll go over it. Az, ax, by, az, ax, by. So these two cancel out. So cross them out. And what are we left with? Well, we are left with, sure enough, 0. And we can do the exact same thing with our good friend b. So b dot a cross b, like that. And we're going to be left with bx times a sub y times bz minus bx times az times by plus, bx az bx. Oh, sorry, that's not bx. It's supposed to be by here. So by az bx minus by ax bz, and I'm just going to write the next one down here, plus let's see, bz ax by minus bz ay bx, right? And once again, these things are all going to cancel out, so let's go over it. Let's see, bx ay bz, let's find the negative. So there's bz, there's bx ay, so these two cancel out. Okay, let's see, by az bx, by az bx. So am I mistaking that? Nope, that looks right. So these two cancel out, and we're left with by bz ax, by bz ax. So these two cancel out, and sure enough, we are once again left with 0. So as you can see with our dot product, that we are in fact getting these 90-degree vectors. So the last thing that I need to go over, or actually two last things I did mention, I'll mention this one briefly, is to look up the right-hand rule, because that'll help you be able to tell if because when you write either a cross x, or a cross b, sorry, is not equal to b cross x, b cross a, sorry. These are not the same thing. They give like the opposites. So if I give these some labels, so if I say that's a, so if I say b cross a is going to be the vector coming out like this, b cross a. And if I say a cross b, that's going to be the vector coming out like that. So this is a cross b. So in terms of actually how to understand which one's going in, or in which direction, which one's like which way, more or less, you need to understand the right-hand rule, which I've actually made a video on. It's about 3 minutes, so it shouldn't take you long to watch it, but I really do recommend that you do. So do look that up. Right-hand rule should be in my videos, or you can find it in other places on YouTube. Hand rule, and that'll tell you which way. The last thing I want to talk about is the magnitude of this all. So the magnitude of the cross product. So the magnitude of the cross product, I'm not going to go over the proofs for this. I just want to mention two things very quickly about it. So a cross b is going to be, and b cross a and a cross b have the same magnitude, but understanding what the magnitude actually is. So it's a, the magnitude of a multiplied by the magnitude of b times sine of theta. So this is actually really similar to the dot product. Sorry, this is magnitude here. It's similar to actually the calculation for the dot product. Of course, this is magnitude, but you'll notice for sure that once again we have the two magnitudes here, and of course if we can do the cross product, then that would make it possible for us to solve, in fact, for sine theta. So that's really dope. We have two ways to calculate for the angles. However, the one thing that I want you to take into account is that when you do sine theta, this actual equation here, some of you may be familiar with it, what it's actually calculating is a parallelogram, the area of a parallelogram. So do my best to draw that out. It's area of a parallelogram. So you have like the length here and the width, and you have the angle. You can get the area A. A is equal to length times width times sine of theta. That's area of a parallelogram. What's important to note is that this angle here, this angle theta, there's actually two thetas that fit for this, and the theta, the other theta, is 180 degrees minus theta, and that's just kind of how sine works, right? So I'll give you an example. If I plug in sine of 30 degrees, I have a calculator in front of me here. I get sine of 30 degrees, sine of 30 degrees is equal to 0.5. And if I say 180 minus 30, that's going to give me, I think, 150. Yep. So I say sine 150 degrees. I'm also going to get 0.5. And I don't even need to plug it into my calculator. I just know. But here we go. I'm going to do it anyway. Sure enough, 0.5. So my point is that yes, you can get the angle between these two vectors. However, there's two, because that's not actually necessarily what you're getting. Because if you're thinking of this as like a vector here and a vector here, what it's doing, and you're taking these two vectors, so let's say this is A and this is B. So if we say B cross A is going to be the vector that goes straight up like this. We're getting the magnitude here is this area, and you'd think that the angle that's between these two is this one that I've got drawn down here. This angle down here. That's the actual angle between the two vectors. However, you have to be careful, because what you might get on it, because there's two separate things, what you might actually end up calculating is the angle up here, which is not necessarily the angle between these two vectors. It's just another angle that works for the sine theta in terms of calculating the area for this parallelogram. So if you really want this angle down here, use the dot product, because it's, in my experience anyway, the cross product always gives you the smaller of the two angles. So especially as you get vectors that are further and further apart like this, right, you're going to get a smaller angle. Like if these two are the vectors here, you might want the angle here, but what you're going to get is you're going to get the smaller angle up in this corner or in this corner. So just keep that in mind, and we'll actually talk a little bit about it in terms of doing what I'm going to show you, which is putting things on angled surfaces, which is also going to take into account not necessarily the calculation that we need to know, but I did talk about it recently, the Rodriguez rotation formula, although we're going to be using the built-in constructor from axis angle in terms of the C-framing, because we're just doing the rotation as opposed to an actual vector rotation. Anyway, I will see you guys in studio. That's enough of the math stuff, so let's actually get into it and let's try some stuff out. Okay, so we're back in studio now, and I'm going to quickly show you let's actually go with the code first. So what we're doing here is we're getting the wood crate. That's what we're doing. We're checking, there's something actually there. This is all on the wiki, by the way. I'm using the exact same example I used on the wiki. We're then going to use raycasting, because raycasting will actually return us the normal, which we can then cross with a vector that's going straight up, as you can see here. Then we can get the angle between these two things. And remember, if we cross those two vectors, we're getting a perpendicular vector now. And if we quickly go back to this, right, if we have two vectors, and I don't have my drop hat here, right? If we have our two vectors like this, and we want to go circular around them, like that, as we learned with Rodriguez rotations, then what we need is we actually need like an axis to go around. So if we can get an axis that's like straight up or straight down, like so, that's 90 degrees to both of these, 90 degrees here, 90 degrees here, whatever, either one, then we can rotate around this guy. So that's what we're doing in terms of the cross product, is we're rotating around this crossed thing. So as you can see, we're just doing some basic positioning, and then we're doing the actual angle with the from axis angle constructor, which, as I mentioned, is just axis angle Rodriguez rotation thing that's built in, but that's specifically for rotation, so can't actually do like the movement angle type stuff that we did with our actual manual formula, but it's what we need for this particular purpose. The other thing we need to be careful of is we need to make sure that the magnitude of the cross product that we're getting is not equal to 0, because obviously if we don't have a vector to rotate around, then things are going to go wonky. So we just pick like a vector, like this has an x. This, if you're not familiar with that, it's just that. Otherwise, we use the unit vector of the cross product to do our Rodriguez rotation type thing around, and we use, of course, the angle that we calculated here. So the main flaw, if you will, in this is just more or less two things. It's lazy ray casting. So, for example, if I do this, it's because it's shooting right down, right? It's not hitting any surface, so it's not going to rotate to this surface, so you could fix that. But even then, and I don't think this is, yeah, it's not going to work for this. If I did do that, right, and let's see if I can quickly fix that. So we're doing where we cast the ray from, where we cast the ray to. I would say, I think it's mouse dot unit ray dot direction. I think that would work. I could be wrong on that. Yeah. Did I spell it wrong? Oh, I might have spelled it wrong. Direction. Like that. Maybe this will work. If this works, then we're in good standing. Okay, so that actually did work. So I'm not sure. So I guess it's not hitting the surface in this. I'm not going to focus too much on this because I don't want to spend too much time. But the main problem, as I mentioned, going back to this thing, going back up here, is that there's two angles. So, and it's going to always favor the smaller of the two. So as we would have seen down here, where the normal is kind of going straight down, facing more downwards, and we're crossing it with a vector that's going straight up, we would have gotten a smaller angle. So the rotation would have been off. So what my recommendation would have been for this particular case would be to actually get the cross between these two vectors, or the dot, so it'd be math dot acos, sorry, between these two, so dot these two, and that would have been my recommendation. And this will give us, of course, the same result, but if we were to do this like under here, and of course my mouse was in fact working correctly, then things would be correct. They'd work. So yeah, maybe it's because the direction is just so short. Let's try multiplying it by like 50 or something like that. I'm really curious, actually, like almost to a degree, why this isn't in fact recognizing. Perhaps we can do game.workspace.current camera, C-frame, look vector. I can only hope. I just can't seem to get the ray to recognize that. So that's unfortunate, I suppose. But anyway, I'm not going to fight over it. I just don't want to focus too much on that because the video is already getting long as is. So you get the point, though. If you could get the ray, which I'm not going to focus on too much in this, then the dot product method would work, and the arc sine method would give you messed up angles in some cases. So anyway, thanks for watching. Hope you learned something new. I'm going to provide the wiki page because any code that I did in this is already available on the wiki. There's no point in uploading it again. So hope you guys enjoyed watching, and thanks.